Welcome back. We're calculating cell potentials again, so the voltage that comes out of our reaction, and we've got three of them here to work out. And they start us off with something pretty simple. We have zinc metal reacting with iron 2 ions. The zinc oxidizes to zinc ions, and the iron 2 reduces to iron metal. So let's see what we'd expect for a voltage from that. One of our reactions is zinc metal converting to zinc 2 ions. So we have to find that in our redox table. And what the redox table offers us is zinc ions turning into zinc metal, which is the opposite of what's happening in our cell. So if ion to metal has a voltage of minus 0.76, then that same reaction going in reverse from the metal to the ions should be plus 0.76 volts. So this orange part of the reaction, I'll just write it as a separate half reaction, zinc turning into zinc ions and releasing 2 electrons should give us plus 0.76 volts. The other half of the story is iron 2 ions reducing to iron metal, or elemental iron if you want to call it that. So iron 2 picking up 2 electrons and turning into iron. Let's see if that's in our data book. Spoiler, it completely is. Iron 2, here we are. Voltage is minus 0.45. And we're taking this one as it's written in the book from the ion to the metal, so we take this voltage as written. It's negative 0.45. So the iron part contributes negative 0.45 volts. When we add these together, we add the voltages together, and we get a total of positive 0.31 volts. So what is the cell potential? 0.31. Is this reaction spontaneous? Yes, because we came up with a positive voltage. Anything that's positive will happen spontaneously. You just get these chemical species in contact with each other, and the reaction will start all by itself. No need to push it. Okay. This next one, we have chromium metal turning into chromium ions and aluminum chloride turning into aluminum. Now, looking at the oxidation numbers here, in AlCl3, the chlorines would be minus 1, each total of minus 3, which means the aluminum is the plus 3 ion. And for the same reason in chromium chloride here, we have minus 2 from the chlorine, so the chromium must be plus 2. We need this so we can find the right half reactions on our redox table. The chlorides aren't really doing anything here. They're negative 1 before and they're negative 1 after, so they aren't doing anything redox. What's the real stories here are chromium metal turning into chromium 2. Of course, that'll release 2 electrons. The electron count is not all that important in these questions, but I'll try to be a good boy and include it. And the other half of the story here is aluminum ions, Al3+, pick up 3 electrons and convert to aluminum metal. So, what voltages do we expect from those things? Chrome to chrome 2. I should mention, because I'm a chem teacher, the element's proper name is chromium, and everyone who says chrome is naughty. I get lazy and say chrome a lot, but if you want to be a good chemist, don't follow my bad example here, call it chromium. Chromium 2 reducing to chromium is minus 0.91 volts. Now, notice what we have here is the opposite of that, so plus 0.91 volts. When you flip a reaction, you flip its voltage. Plus 0.91 volts for the chromium side. The other thing happening is aluminum ions turning into aluminum metal, and that one's pretty low down. Here we are. Minus 1.66 volts for the ion turning into the metal. And what we have here is the ion turning into the metal, so we get to keep that voltage as is, minus 1.66. when we add these together, we get 0.75, negative 0.75 volts would be our total. And that is definitely what it says on the solution line down here. This is obviously a 5. If you thought it was any other number, you are mistaken. I'll have to correct that before we publish the workbook. Okay, so those are the two voltages. Find the voltages. If a reaction is flipped, flip its voltage. When you add the half reactions, add their voltages. Nothing too bad, I hope. Now, this last one is a little complicated and a little bit weird, but I decided it's not so weird that we have to get rid of it, so let's see if we can deal with this thing. Silver nitrate reacts with hydrogen peroxide. We get silver metal, nitric acid, and oxygen. Now, nitrate ions are super soluble. They dissolve wonderfully in water. You can think of it like they wash off very easily from anything when they're put in water. So silver nitrate you can think of as silver ions and nitrate ions. Those will dissociate the moment they get wet. And then we have hydrogen peroxide, H2O2, arrow, and then we have silver metal. Nitric acid, same thing. This will dissociate instantly into hydrogen ions and nitrate ions. Nitrates just don't stick to anything incredibly hard. And, of course, we get oxygen gas. That doesn't dissociate. That's a molecule. So, these are the species before and after. And now you can see, for our redox story, we have silver ions reducing to silver metal. That's one of our half reactions. Ag plus a single electron turns into silver. And the other side of the redox story is H2O2, hydrogen peroxide, turning into hydrogen ions and molecular oxygen. Now, the silver reaction we've probably seen before. We do silver cells kind of often. And here it is. Silver ions going to silver metal is plus 0.80 volts. So, filling that part in is no trouble at all. Switch pen to red, 0.80 volts. Now, this peroxide thing we do not see a lot at all, but H2O2, 2 hydrogen ions, and oxygen is indeed in the data book. And I'll even find it if you give me a second. Here we go. This is the opposite of what we have, so there's a flip involved here, but H2O2 will convert to an oxygen molecule and 2 free hydrogen ions, and you get 2 electrons on the hydrogen side as well. If it's going towards the hydrogen peroxide, we get plus 0.70 volts from this, so if we're starting with the peroxide, if we're doing this in reverse, we're going to get minus 0.70 volts. So it's not too disorienting having me zip back and forth like this. I'm trying to interact with the book a lot so that you see how important the book is and get used to interacting with it. Let's put the 2 electrons in here, just 2 electrons plus all the other stuff. Okay, so this reaction was flipped, so we flipped its voltage. Now we add these voltages together and we get positive 0.10 volts. And because that's positive, we'd say that reaction is spontaneous. Hope that wasn't too weird. We have the nitrate ions here, which we'd consider a spectator because they didn't oxidize or reduce. That means they just don't interest us when it comes to determining what the redox reactions were. That happens sometimes. You have some substances that get reduced, others that get oxidized, and some that just stand around watching. In this case, the nitrate just stood around watching.